Right. So welcome to RISE Learning Machines seminars. I am Olof Mogren, and I'm a researcher on foundational and applied machine learning at RISE. RISE is Sweden's public research institute, and this is our open weekly seminar on AI and machine learning. This meeting will be recorded, and let us know if you want to be removed from this recording. Also, check out the collection of great talks that we have on our YouTube channel. Today, I have the pleasure to introduce Newton Mwai Kinyanjui, who is a PhD candidate at Chalmers University of Technology within the Healthy AI Lab. Newton is supervised by Fredrik Johansson, who incidentally was my colleague when I was a PhD student at the same place. Newton works with machine learning to improve sequential decision-making in healthcare using historical data. And the topic today is improving treatment personalization with structures in sequential decision-making, as you can see on this slide. And with this said, I will stop my speaking and hand over the floor to you, Newton.
Hi, everyone. I'm happy to be presenting this talk today. The talk is titled Improved Treatment Personalization with Structures in Sequential Decision-Making. And to begin, let me see, this works. Yeah. To begin, oh yeah, sorry. Yeah, right. So to begin, I will introduce treatment personalization. And essentially, treatment personalization involves using individual patient characteristics to identify what the optimal treatments for this individual will be. And these treatments could be from a very large number of possible options. And also another thing about this decision-making process is that it could be sequential. So you may want to find the optimal treatments when you don't initially know how the patient responds. And the way you will do this is to try them sequentially. So try all the possible treatments sequentially until you can confidently find the optimal treatments. So treatment personalization can be seen as a treatment search, where you have a set of treatments, and each treatment induces some sort of value or reward when the patient takes it. And your goal then will be to try the treatment sequentially until you can be confident that you are giving the patient the optimal treatment, the optimal treatments. So there's two goals that one could aim to solve with this formalism. One of them is to maximize the patient outcomes over the patient's lifetime. So the treatment never stops. It could be theoretically infinite, but of course, this is limited by the realistic lifetime of a patient. And the goal here is to find a policy that maximizes the outcomes over the lifetime. Another way one could see this process is as finding the best treatment as fast as possible. And this is a bit different from the first objective, because here the objective will be to just gather information from the treatments to try and estimate which of the options is the best treatment. And once you find the best treatment, you stop. So you can think of this as a process where you're trying to find the treatment with the highest value. And once you find it, you stick to it from the stopping time, and the patient receives the reward, or that rather the value corresponding to that one treatment. So these are problems that have been formulated and researched for a long time in multi-arm bandits. And this is the formalism that I mainly use for my research. So I will start by introducing multi-arm bandits so that we can, before we go to the specific problem formulations. Right, so what are multi-arm bandits? So multi-arm bandits are a sequential decision-making approach where you have an agent, and this could be seen as the personalization strategy, which interacts with an environment over a number of rounds. And the agent is choosing actions from a set of possible actions in turns. And every time it chooses a possible action, an outcome corresponding to the action is observed. So to note here, the rewards are defined by some known probability distributions, but the respective parameters of the distributions are unknown to the agent. So the agent is trying to estimate the parameters of these distributions. So how a multi-arm bandit algorithm will look is that there will be a couple of rounds. So T is equals to 1, 2, all the way to T. And at each round, the agent chooses an action using an exploitation strategy, and an independent and stochastic reward is drawn from the distribution corresponding to the action chosen. And once you know once you observe the reward, you can now make parameter updates to your estimated distribution parameters. And this continues over and over again. So depending on whether you're in the first problem where you're aiming to maximize the outcome, or in the second objective where you're aiming to find the best treatment, you will update parameters accordingly. In the first objective, where you are not limited in when you need to stop, and your goal is to maximize the outcomes, you need a way to measure the performance of your strategy. And this is measured typically by a quantity called regret, which can be seen as the expected deviation of the agent selecting suboptimal actions over the process. And in this formalism, or other in the regret minimization, the agent aims to minimize this regret, or the regret of choosing the suboptimal actions. In best term identification, which is a related but a different kind of problem, the agent aims to minimize the stopping time, and the stopping time is the time at which they are sure that they found the optimal action. And this is defined by being confident with a given confidence level that the action that they're choosing at the time of stopping is the optimal action. So this is one of the ways that best arm identification tries to think of this problem. There's other formulations called fixed budget few exploration, but this, where you have a given confidence parameter, is called fixed confidence few exploration. And this is what I've been mostly looking at during my research. And you may be wondering what this strategy looks like in best arm identification. So to give a brief outline, strategy comprises a sampling rule, which selects the actions over the rounds, a stopping rule, which decides when the exploration is over, and a recommendation rule to return a guess for the best arm once the stopping rule says you can stop. Okay, but how do we do personalization with bandits? So in personalization applications, you need to find best action given a particular situation, which means that you need some sort of context which defines these characteristics. And there is an extension to a general extension to the bandit formulation where the problem is augmented with context, which is a vector from a d-dimensional vector. And now the reward is drawn from a distribution that is a joint distribution of the context and the actions. One thing to note about contextual bandits is that the action does not change the context and it only contributes to the reward. So this is a bit different to the more general reinforcement learning setting. But it's still useful for treatment personalization in chronic diseases. For example, in rheumatoid arthritis or in Alzheimer's, where you cannot completely eliminate the disease, you can only treat the symptoms. You could still apply these, you could still apply bandits in solving the problem. A pro of using contextual bandits is it can allow us to achieve very high personalization for a given context. But the problem with contextual bandits is that they typically take very long to explore. And these can be impractical in real-world clinical settings. Okay, so that concludes like a bit of a background. And now let me give a brief outline of the research that I've been working on during my PhD. I'm mainly interested in treatment personalization with bandits. And as I said, this is suitable for chronic diseases like Alzheimer's disease or rheumatoid arthritis. And the main directions I look into is designing sample-efficient treatment personalization algorithms. And here I think of how we can use historical data to be sample-efficient. And I also think of designing treatment personalization algorithms with real-world exploration constraints. For example, there may be costs associated with switching treatments. And also, I think about how we can build realistic simulators for observational data. And that can give us good simulation environments. As you know, working with healthcare data is quite challenging regarding the access and everything around it. So I also think of how we can still do the experimental work. Great. So let's get into the into the crux of my presentation today, which is in structural treatment personalization. And you may be wondering, so how do structures appear in treatment personalization? So in my mind, we can see structures in three different aspects of the treatment personalization problem. So the first one being in the response of patients to treatments. So one example could be that there are groups of how patients respond to treatments. So the response to treatments could be seen as grouped, and this grouping could be known, but more realistically, it is more realistic to not know the groupings of how patients respond to treatments. I think another structure that one could think of is in the exploration process itself. So for example, when you have constraints on how you can explore, you could possibly use structures in designing your exploration process. So the structure here is induced by the constraints that come with the problem. As an example here, if you have costs in switching treatments, you cannot feasibly switch treatments at every time step. So you will need to design a way of assigning treatments successively. So that is the kind of structure I'm thinking about here. Another way that structures could appear in this problem is possibly in the treatments themselves. As an example here, so these are example therapies, say from a physical therapist. I have this example because I did this last year for my shoulder injury. So imagine you have three exercises that the physical therapist assigns you, and you could see this. So the way the structure could come about here is that the utility of doing one exercise, if you haven't been doing another exercise together with it, could be higher than the utility of adding an exercise to maybe two initial exercises. This structure is called submodularity, where there is a diminishing returns in the marginal gain of adding items to sets, or yeah, to these kind of collections. I will mainly look at the first two today, and possibly in the future I can come back and talk about the third one. Great. Do you have any questions before I continue?
These structures, are they things that you observe in the different applications that you have?
Yes. So for example, the structure in the responsive treatments, for Alzheimer's, it is known that there are groupings of patient types in Alzheimer's, and these patient types could respond to treatments similarly. Only that you typically don't know what a patient type a person is, so you will need to estimate it. And if you know the patient types, then instead of complete personalization, because essentially the patient responds similarly, just defined by their patient type, you could personalize for the groupings, which could potentially be as good as complete personalization while saving you sample efficiency. So the second one is a constraint that is very realistic. For example, in clinical trials, before you start a new treatment, you have to have like a washout period. I mean, when the doctors are assigning treatments, they typically don't give treatments like for a day. They give treatments like, I don't know, for a long time. So you're essentially taking the same treatments successively. So these are indeed observed in the problems, healthcare problems. Okay. Right. So let's look at the first kind of structure, which is in patient grouping, and how could we use historical data for this kind of structure. And before that, let me introduce latent bandits, because there's latent bandits in the title there. So latent bandits are a bandit setting where the rewards are influenced by some unobserved factors, which is latent, the latent state here. And typically, studies in latent bandits have assumed that there are discrete latent states. So essentially how the problem changes is, instead of having just K probability distributions, now you will have S by K probability distributions. And another very strong assumption that is typically seen in these kinds of works is that these conditional probability distributions are available. They have been estimated a priori. So that in the learning problem, the problem that you will be aiming to solve there is just estimating the latent state. And then once you find the latent state, you can identify the best treatment straight away. So a latent bandit problem algorithm, the algorithm or the agent observes the context. They estimate the latent state. Once the latent state is estimated, the optimal action can be selected. An action can be selected. A stochastic reward is realized from the distributions. So this is the S by K distributions. And you make the parameters until at some point you're sure enough that you have estimated the correct latent state. Okay. Right. So back to our latent bandits problem. We also assume that we have a latent reward model available in this work, similar to previous work, but this assumption is we have some problems with it. But for this work, we assume that we had a latent reward model already estimated. And this latent reward model essentially is a joint distribution of the latent states, the latent states given the context, and the rewards given the latent state and the actions. In addition, latent bandits also consider the context still in the reward model because they assume that there could still be some information in the context that is informative to the reward model, but probably most of the information is in the latent state. And we also assume that patient heterogeneity is still discrete. And now our problem in this work is, can we incorporate the latent reward model in the base term identification problem? So this kind of formulation had been previously unstudied. And this diagram illustrates our problem formulation more completely. So we assume from historical data, the latent reward model can be estimated. And now for a new patient instant, we just aim to estimate their latent state. And once we estimate their latent state, we can use that to find the optimal treatment. And as I said, the patient type or patient heterogeneity is discrete in this case. More specifically, now we aim to estimate the stopping time. Remember, this is base term identification. While finding an optimal action for a given latent state, given the context and the latent state. So we aim to design a such strategy to minimize the expected number of trials required to identify an optimal action with a high confidence for new subjects with observed context and an unknown latent state. Our assumptions, as I said before, we have access to a true latent variable model, and the latent state is stationary, so it doesn't change over time. And the context here is also assumed stationary. So how do we incorporate these latent structure in the solution? So we have S by K distributions with some known parameters. These have already been fixed. And for a new patient instant, we don't know the latent state, and we need to estimate this first. So how could one estimate these latent states? One could aim for estimating the true latent state, or one could aim to identify the set of latent states that have the same optimal arm. Remember that the objective in best arm identification is to just find the optimal arm and you stop. And there could be latent states that have the same optimal arm. So the first option is sufficient, but it's not, I would say it's a much stricter solution to the problem, as identifying the set of latent states that have the same optimal arm essentially solves the problem. So it's kind of loser, but it still gives you an optimal arm. And ideally, the second solution could lead to like faster stopping compared to the first. So we aim for the second solution in our problem. Our strategy to estimate S is to play minimum trials using arms which distinguish the latent states the most. And how do you quantify these distinguishing of latent states? You could think of these as the latent states that that yield sorry. You will think of these as latent states that give you the highest, the lowest, wait, I have to figure this out a bit. That give you the highest KL divergence between two latent states. So the KL divergence is a measure between a measure of distributions that is typically used in information theoretic approaches. Right. So you aim to play arms which give you the most information. That is the point I'm trying to make here. To understand our solution a bit better, I'd like to introduce a notion of what are optimal best arm identification algorithms. And a good strategy in best arm identification is one that aims to be as close as possible to a theoretical lower bound on the stopping time. So when you're stating the problem formulation, you can, to solve the problem, you can start by first deriving a theoretical lower bound for what is the best possible time you will achieve for your problem, given all your problem characteristics. So in our case, the characteristics being that we want to distinguish latent states. Great. We want to play arms that are giving us the most information. And this will give you a theoretical lower bound on what is the best achievable stopping time for that problem. And once you find the lower bound, you could get proportions of what could be the optimal proportions to play the arms until stopping. So given a stopping time, how many times will you play each arm until the stopping time? And these proportions are the key quantity that are typically used to design algorithms. So there's a set of algorithms called track and stop algorithms, which track these optimal proportions. So these are optimal proportions from the lower bound. So you establish a goal of proportions, and then you design a strategy that aims to play arms in as proportions as close as possible to the proportions from the lower bound. And essentially what this is doing is to minimize the deficit of the played, sorry, I think there's a typo here, of the arm plays up to a time point. And I think we will see this shortly. So we design a similar looking algorithm whose proportions are defined by objectives of distinguishing latent states the most. Okay, so what will the proposed algorithm look like? Remember the three key ingredients of an algorithm in a best-term identification problem. So we have a sampling rule. And as I said, an optimal algorithm aims to minimize the arm play deficits. And if you look at this sampling rule more closely, you will see that essentially what you're trying to minimize here is the arm deficits between the number of plays of an arm and what will be the arm plays from the lower bound proportions. And then we have a stopping rule. As I said before, a stopping rule defines when are you sure that you have found a good arm and that you should stop. And our stopping rule here is that we are confident enough that given the posterior of over the latent states, we have found the best arm. And a recommendation rule is essentially a rule that selects the action that has the highest mean from the estimated parameters under a given latent state. Right. So does using this kind of grouped latent structure help in exploration? And indeed it does. So comparing our algorithm, the blue one that has a latent structure, to previous algorithms that don't incorporate latent structure, you can see that there is a massive gain in the stopping times that could be achieved, which is a good thing. It's a great thing for treatment personalization. But as I said before, we have assumed that in these in the previous work that we have access to these latent reward models. But it is a bit unrealistic because, I mean, for different conditions, different kinds of data sets, I think you will be a bit too optimistic to assume that you have, that the problem always comes with a latent variable model, a latent reward model. So in current work, what we're working on with my colleagues is to recover the latent reward models from historical data. And essentially this involves learning latent variable model and finding some conditional average treatment effects conditioned on the latent state. So stay tuned for this. We are currently in the submission process. And hopefully I can get to talk about this more in the future. Okay. Let me know. But before that, do you have questions here? Yeah.
What's the data that you build results from?
So for this, the data that I showed results for is results from a semi-synthetic data set from the ADCP environment that I mentioned before. And essentially the ADCP environment is a longitudinal environment made with Alzheimer's data. So we have sort of handcrafted some features, but a lot of the information in the data is from like a real world data. So the data didn't come with interventions like with treatments and latent states. So we had to incorporate those into the environment. So it's quite close to being realistic. Yeah, yeah. So the treatments, we found them from, there's a lot of Alzheimer's literature on clinical trials and what are the average treatment effects of treatments. So we used Alzheimer's literature to. Yeah.
effects and then
Exactly. Yeah. Yeah. I didn't get the last bit.
Use the literature and the data and something to
Yeah, exactly. And they didn't have any treatments at all.
Okay.
Yeah. Yeah. Yeah.
Okay.
Yeah. 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 So yeah, we added the treatments from Alzheimer's literature and corresponding. Yes. And we also had, so from Alzheimer's literature, we also found some kind of policies that could be seen in healthcare. So there's actually people who have designed policies and given coefficients of like a realistic policy that could be in a clinical setting.
If the algorithm, you don't need to see the actual effect of the treatment.
You will need to see a treatment effect because that will be your reward. Yeah. So now we added the treatments to the data and they come with a treatment effect. Yeah.
The rewards or the outcomes of treatments are based on clinical trials that yield the average response that so those are going to cost. The treatments were decided, as we say, based on policies that people estimate how common is each drug for each kind of person. And then the individual variation is this effect. So again, how do we deviate from the average effect?
Worst is as that first help to
exactly. Exactly. So yeah, these are latencies that are very similar. So it's a bit hard to distinguish. But still, I mean, they're still pretty close to the lower bound. The stepping terms.
What the other question is the classification.
Yeah.
But I think we should go on.
Yeah. Okay. I'm going to move on to the next kind of structure that I sort of introduced. And this work now is titled Patched Fixed Confidence Pre-Exploration for Bandits with Switching Constraints. Right. So the key point in this work is that there could be switching costs associated to the exploration process. So every time a treatment is changed, patient must get used to a new treatment and side effects. And as I said, in clinical trials, we may have some sort of washout period where you're not taking a drug. So can we sort of introduce a constraint for switching in best-term identification? Essentially, the goal of this work is to have like a realistic kind of exploration for the real world. And the way we formulate this problem is by using batches in exploration. And I will explain shortly. So typically when you explore, you switch treatments every time. So you're not constrained in how often you can switch treatments. And your goal is to explore as much as possible. So you're unconstrained in switching and you want to explore as much as possible. So essentially what this does is it encourages you to switch an action every time. Okay. And now we say, what if you had like a switching constraint or a switching cost? Remember the original objective in best-term identification, minimize the stopping time such that when you stop, you found an optimal treatment with a high confidence. We additionally add a second constraint such that the expected switching time, or rather, such that you have like a constraint on the switching rate. And this is a bit conflated. It's a bit hard to see how you can intuitively solve this problem. So we reformulate this problem to be in a batched formulation, where we say, how about if we minimize so we batch the exploration, and we say, let's minimize the number of batches until we can find an optimal action. And then how about if we have a switching constraint? How about we make sure then that the number of switches inside the batches are low? So this is now the second constraint that sort of is a proxy for solving the switching rate constraint that we have in our problem. And this is a solution to the first problem. So the idea is to, as I said, to batch the exploration and ensure that the number of switches inside the batches are small. And we assume that this switching constraint, or the number of times you can switch inside a batch, is provided. And we know, like, the batch size that you will want to split your exploration horizon in. So in this diagram, essentially you have played the arms the same number of times. So remember, we just want to find the optimal action. So it doesn't matter if you switch every time or you play them consecutively. All that matters is that at the time you're stopping, you have found the best arm. So you can play them consecutively, making sure that there is minimal switching, and still find the best arm. Right. So we aim to minimize the stopping time while limiting the rate of switching arms to some alpha. And this is solved by reformulation into a batched bandit problem. And as I said, the batch size and the switching cost is provided. Right. So what is the solution pathway? So remember that track and stop algorithms track the optimal place for each arm at each step. And as I said, as I highlighted before, essentially they are tracking how far behind an arms are. So they are tracking a deficit of how far behind is an arm from the optimal proportions. So we say, instead of tracking the optimal proportions at each time step, how about we track them per batch? And then, because we only want to play S+1 arms, we provided with a switching number, or like a switching limit. We want the batches to play sparse proportions of the arms. So we only want to play like a subset of the arms in a batch. So we want sparse proportions in the batch. So one way you could solve this is, the batch size and S. Theoretically, you could enumerate all the possible ways that you could play the arms given these two parameters, but these are very large number, and practically it's not feasible to enumerate it. So essentially, algorithms aim to find an efficient way to construct these configurations. So the key point is we track the deficit and construct and design a way, or devise a way of constructing the configurations instead of enumerating them all before. So this deficit, somewhere in there is some proportions that have been derived from the lower bound. Yeah, so this is the deficits. What you aim to construct is the configurations, and these and we are minimizing we're aiming to select the configuration that minimizes this deficit. And this is a positive deficit, so to say. So just keep track of the arms that have been left behind. And as I said, somewhere in the deficit, there is some arm proportions. And empirically, we see that we can stop quickly, even with a very strong switching limit. If you look at the thickness of this line, so you can see that most of our stopping times lie somewhere towards the earlier side of the graph. And another interesting result is that we can be able to match the optimal and batched algorithms quite well. So the one in light blue is the optimal and batched algorithm, and the orange and blue are our algorithms, and we match them quite well, although we suffer intuitively having like a very large part size. At some point, you're going to suffer. Good. So, I think we're running a bit out of time, but this is not so bad because this is my last slide in content. And now I'd like to highlight my collaborators. Of course, this work wouldn't be possible without working with people, including Frederick, Yamil, Ahmet, and Milad, who I thank very much for their insights, and it's been fun working with them. And with that, I will open the questions and discussion. Yeah. That is a good question. So the orange one is one. So we're aiming to construct a sampling rule that essentially solves this objective. And what the first one does is it is a greedy selection rule, which constructs these configurations greedily. So the solution to this objective is not unique. Has many feasible configurations, but it can be solved polynomially. So the first one, which is the orange one, just constructs them greedily. The second one is one that actually constructs sparse proportions. So the way we construct the sparse proportions is projecting the proportions of the arms onto a sparse simplex. So it essentially just does a sparse simplex projection. So that should just remain with like a number of arms corresponding to S. And it is essentially two ways of solving the same problem. But there are some deviations in how the space that remains in a batch after you clear the deficit for the selected arm is distributed. Yeah, so overall, it's two ways of solving this problem with some deviations of how the space that remains is allocated. Yeah. Yeah. Yeah, they are very similar. As I said, they both solving these objective. Yeah.
Interesting. Also, people online are welcome to ask questions. You can unmute or you can send them in the chat.
Yeah. 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 You could motivate it by saying that they are sort of inspired if you have the domain advice. But you could see cases where you can maybe decide the switching limit, for example, before. I'm kind of lacking at straws here.
This is really different.
Yeah.
I mean, so I was thinking this feel free to jump in here, but so many drugs take longer to start effect, for example, so you'll have a longer switching process since you don't start one of those effects, or it's like sense effects.
Yes. So we have in oncology we have the half-life of the compounds, and I don't know for Alzheimer, but you have some antibiotics where the half-life is several days. So obviously the washout time, we say it's about 7 to 9 half-time. So it could be days to weeks or hours depending on the compound. So yes, there should be some difference in the switching, and also the lag you see on the effects, because you need to reach also a useful dose, and that takes longer than the longer half-life.
So for the ones online, the question was about whether we can know in practice what the cost of switching is.
Yeah. And our pharmacologist colleague has responded.
You may also have cases where you have a strict incompatibility between two drugs. That happens. So maybe you have some switches that you're not allowed to do. Some sequence are not allowed to do in your life, but I don't know for design general experience.
I will wrap up the online meeting there, and thank everyone for attending, and especially, of course, Newton for this interesting talk. Next week we'll have Amal Malushi, who's a PhD student at Karlstad University, and also one of the founders of Africana AI, and she'll be talking about leveraging AI for climate resilience in Africa.